Ready when you are.
Hi, welcome everyone. Brooke, most of you. It's my pleasure this morning to be able to introduce Jonas Juul, who is visiting us from the biochemistry department at the Niels Bohr Institute in Copenhagen. Jonas has been working with Mason Porter, who is a friend of the Network Science Institute, to study various things, including diffusion processes on networks. And today I was excited to see that he'll be talking today about what happens when nodes in the network sort of intentionally subvert popular diffusion processes. So what happens if you choose the wrong product or the unpopular product as a kind of active conscious choice? So it should not be interpreted anything other than the fact that I have a busy schedule. I do have to scoot to teach an undergraduate class, but I'm glad you're all here to watch Jonas's talk, and I'm sure it's going to be great, and I'll enjoy watching the video later. So take it away. Thank you.
Thank you so much. And thank you for showing up, and thank you for having me. Bye-bye. Okay, yeah, so I'm Jonas, and I'm pleased to meet you all. And I'm a PhD student, as was just said, from the Niels Bohr Institute in Copenhagen. I'm in my first year, and I'm here to present a small fun project that I did with Mason Porter, visiting him in Oxford. So he's now both in Oxford, but also in UCLA, in California. And we've been working on this little project that I'll be talking about for about 30 minutes. Okay, so how do anti-establishment elections come to exist? That is a fun question to ask, and a question which many of us, I'm sure, have asked during the last couple of years. Just to show a couple of quotes from media during this last year. The anti-establishment wave that propelled Donald Trump to the White House. This is a quote from Reuters, just 1 month ago. Trump's election is an unmistakable projection of a political establishment. It's Jeremy Corbyn, the UK Labour leader, said this 1 year ago, right after the presidential election. And Czech election won by anti-establishment party led by billionaire. That is a headline from the New York Times a couple of weeks ago as well. So it seems like there's this hypothesis out there in the media that in some of these elections, for example, the presidential election in the US, the Brexit referendum in the UK, and in many other European, especially elections, people don't necessarily choose something they want, but they actively choose something that they really don't want. That's the vote for the opposite thing. So one thing one might ask is how many people do we need to have this behavior in order for the anti-establishment choice to become the major one, to win an election? And this is, of course, a difficult question to answer in real life. So what one could do is start with spreading processes that are well studied, and then implement these anti-establishment nodes. So, do we need a majority to actually choose different from the establishment, or can a few people have this anti-establishment opinion or behavior, and then spread their opinions to other people in the network, thereby creating a majority? That is what we have been looking into this project. So, an outline for this small talk will be, first, we want to choose a simple spreading model, then include these anti-establishment nodes into this spreading model, and then we implement it on several types of networks and see whether it is indeed possible for a few nodes with this behavior to spread the anti-establishment opinions into a large part of the network. Okay, so let's start out with the first point. We choose a simple spreading model. Okay, so there are many different spreading models, and I'm sure that you guys know more of them than I do. I should have talked to a couple of you yesterday. But one that Mason and I liked in particular is the what's threshold model, which came out in 2001. And I'm not sure that you are all completely familiar with this or remember it, so I'll just go through it very quickly. So we have a network of n nodes, and each of these nodes can be either active or inactive. Each node is assigned a threshold from some distribution. So here I draw the thresholds with gray. And the idea is then that an inactive node can become active if the number of neighbors it has that are active divided by its total degree is larger than or equal to the threshold that was assigned to it. So in this particular example here, we can focus on the middle node here. It has a threshold 0.2. That's 1/5. And if we count it in a fraction of the neighbors that are active, it's 1/4. So this fraction is indeed larger than the threshold, and this will become active right afterwards. So it's a very simple model, and one of the reasons why we like it is because it is really easy to extend. One of the ways it might be extended would be to change the way a node decides whether to become active or not. So for example, instead of simply counting the number of active neighbors a node has and divide it by the total degree, one might count the number of active neighbors the node has and take the power to 1 plus beta, where beta is a real number. Then divide that by the total degree to see whether or not this is larger than or equal to the threshold. So this is just one example of an extension of the model that has been made, and Mason and I did this as well, and this paper is in archive as well. So the model is deterministic, meaning that if you start the process, if you infect some or activate some nodes at time 0, it is given which nodes will become activated when you let time go to infinity, and then the nodes update several times. And this also makes it tractable often to get analytical results for the spreading process to see how many nodes have been activated at a given time t in the future. And this holds even for the extensions. So just to sort of look at this extension, which is another one, what I'll do in a minute. What we did with this extension was activate some nodes in a network with 2 different kinds of nodes. Nodes with a low threshold that were easy to activate, and some nodes that were more difficult to activate. Then we asked, in steady state, when we let time go to infinity, how large a fraction in the network of each kind of node is then active. And we got, as a function of beta, we got this diagram here, where you can see that there are these abrupt jumps, and we were able to find an analytical formula for this that caught these abrupt jumps as well. So it's just to it's just to show that you can easily make extensions, and often it's tractable to get analytical solutions out, even with the extensions. Okay, so that's something that we hope to do because Mason is an applied mathematician, and it's fun to do analytics. Okay, so what are we going to do then? So we've chosen our framework, what's the threshold model, and now we want to implement these different kinds of nodes. Nodes that act normally, so they choose the decisions on depending on their nearest neighbors, and then these anti-establishment nodes that look at total population and deliberately chooses differently from the majority. So this is what we're going to do. We're going to consider a network in which two competing products, it may be yes/no opinions in a referendum in the UK, it may be presidential candidates or other things, whether to buy CDs or vinyls, something like that, spread in the population. Each node has to choose which product to adopt when it gets activated, as it does in the watch threshold model. And some of these nodes act normally. They adopt what most of their friends, their neighbors, already adopted if they adopted a product. And some of them, so I randomly drew these with the red caps on them. They adopt what the least people in the total network. Okay, so these two kinds of nodes. And at this point, just take a little step back because okay, before taking a little step back. Okay, so these nodes need information of the total distribution of products in the network. So it's natural to assume that this information might be delayed somehow. They may not instantly know how the distribution is in the network, but maybe they need some time for the information to come. In an election, this is how it works, right? The newspapers call, or the institutes call people, ask them what they want to vote, and then some days after that, they publish the results, and then we know what's popular as well. Okay, so now we want to take a step back, because these two kinds of nodes that act, that want to look like their neighbors, and nodes that want to look different from the majority in the total population, already have been studied in other systems. So for example, there's this cool paper called The Hipster Effect, when anti-conformists all look the same, which is on arXiv, put there in 2014. And just to get an idea of what the author of this paper to study, just quote something from the abstract. In such different domains as statistical physics and spin classes, neurosciences, social science, economics, and finance, large ensembles of interacting individuals taking their positions either in accordance, mainstream, or against hipsters, the majority are ubiquitous. Yet, trying hard to be different often ends up in hipsters consistently taking the same decisions, in other words, all looking alike. So, this paper introduces a spin model in which grid points want to either look the same as the grid points around or different from the majority. And this ends up causing these grid points that don't want to look alike actually looking alike. So just because this, and the idea here is that that these grid points have a delay in information as well. So the grid points in this model are actually pretty similar to the anti-establishment nodes in our model. So just to be consistent with the words that we're using in the field, we will from now on refer to the anti-establishment nodes as hipster nodes. Here drawn as a typical hipster in San Francisco, Copenhagen, or maybe Boston, I don't know. Okay. So now we're ready to sketch the total club. We have a network, and in this network we have nodes. Each node has a probability, it's called p-hip, of being a hipster, and a probability 1 minus p-hip of being a normal node. No matter what kind of node is inactive, then it can get activated if a fraction of its neighbors that are larger than or equal to its threshold that it's assigned to it is so if the number of active neighbors divided by its total degree are larger than or equal to its threshold, then it becomes active. And if it gets active, it must choose what product to adopt, product 1 or product 2, two different products. And a conformist chooses to adopt the product which most of its neighbors have adopted. And a hipster node chooses to adopt the product which is the least adopted product in total at some previous time. So a conformist looks at its distribution of products at t time t minus 1 choice, so the previous time, and over here they look at the total distribution at t minus tau, and if tau is equal to 1, then there's no delay in the information. If it's larger than or equal to 2, then there is a delay. That's the model. So let's carry on with the simulations. So we choose a network, we choose, yeah?
With the model, you'll never like change the connections between the nodes, right?
That's right.
Because I can also assume if a node is a hipster, they might also change their social ties to connect with other people that has shared similar interests.
Indeed. So at this point, we just make our assumptions as simple as possible, I'd say. So extensions like these phenomena where hipsters group together, or where maybe you have big social media channels that have specific opinions. And, I mean, so you can definitely make correlations about this hipster quality and then the different nodes in the network. But for now, let's just look at it in a totally random way. Yes, so we choose some network, and we choose a delay times tau and a probability of a node being hipster. And then in all of our simulations, we activate a single node at the beginning of time, and let this node have product 1. So if there are no hipsters in the network at all, then product 2 will never get adopted. So that is an anti-establishment choice to make. Then we update our model in discrete time. We've also done some simulations with continuous time, and it seems to change the outcomes. And we let our simulations run long enough so that there is a steady state in the simulations. Okay, so let's jump right into it and start the simulations on a Facebook network. On the Facebook 100 dataset, this is the Northwestern 25 network. A little more than 10,000 nodes in it. So here we have different parameters. We have one parameter pair, in which the probability of a node being hipster is 0.04, and the delay is 1, so not existent. And we have another parameter pair here, where the probability also is 0.04, but the delay is larger, it's 4. And in this case, we see that the two parameter pairs, the simulations with the two parameter pairs behave the same. So we have a large fraction of nodes adopting product 1 in both of them, and a small fraction ending up adopting product 2, which was not introduced at time 0. So if we choose some other parameters, here we choose the probability of being a hipster to a large number, 0.3, and then the delay being 1, that's non-existent, or 4, which is a larger delay. You see that there is a different behavior for the two parameter pairs. So with no delay at all, equally many, more or less, end up adopting both products, each product, and with a larger delay, then product 2 succeeds and is adopted by most. So it seems like both parameters change the overall behavior of the system. So just with this initial simulation, we'll now dive into more rigorous simulations, parameter scans on different network types. We'll start out with a very simple case, a 5 regular network with two different two different thresholds. One which is very low, which makes it possible for a node to get activated even if only a single neighbor is active. and another one which is high, so that a node needs 4 neighbors to be active in order to get activated itself. Okay, so here we have, this is the behavior for tau equal 1, that is almost no delay in the information that the hipsters have total population product distribution. And we see that for very small probabilities of being hipster in this information, there is a rapid increase in the number or in the fraction of nodes that have adopted product 2 at steady state. So we only need around 90% of the nodes to be to have this hipster quality, anti-establishment quality, in order for product 2 to get as adopted as product 1 at steady state. And for larger probabilities, we see that that the hipsters just even out the distribution, so that we have a 50-50 adoption. Okay, and increasing the delay a little bit gives us the same result for small probabilities of hipsters. So around 10%, 9-10%, equally many have adopted each product. Then there's a small interval here in which product 2 gets adopted the most. And then there are different intervals in which each product dominates. So in this case, there are 3 intervals in which product 1 dominates and 2 in which product 2 dominates. Also, we see, so we made an analytical, a very easy analytical approximation, which we see behave like the simulations for small fractions of hipsters. So these are the blue ones here. The blue ones are the expected number of fraction of nodes that have adopted by product 2 as time goes to infinity. So we see that it behaves like the simulations for small fractions of hipsters, but then afterwards we get these abrupt jumps in discontinuities in the solution. So if anyone has a good idea how to solve something like this in an analytical model, then please tell me. It's very easy to do this. We basically just calculate the probability that some node will be active at some time, and the probability that it has had more neighbors with one product than the other, and then include the probability of the node being used. And then do this in a recursive manner. Yeah. So you can look up the paper if you're interested in details. Okay, so increasing the delay in the information that the hipsters have about the total population makes let's get a little bit more information. So again, we have these abrupt or really rapid increases in product 2 adoption, and then we notice this first interval in which product 2 becomes the most adopted, and the peak of this product 2 distribution seems to increase with delay. So the larger delay, the larger difference between these two curves. And then there's a non-trivial behavior, I think, in how many intervals in which each product dominates. Yeah. Again, we see the abrupt jumps in the analytical approximation, but at least it's sort of gets right which product is the largest at one point. Okay, so that's all I wanted to say about these, and just by increasing a little more the delay, we see the exact same pattern, rapid increase. This peak here becomes higher with the delay, and the analytical approximation still does better. So, so that's more or less what I had to say about 5 network. And what I'll do now is just take a couple of other types of networks and see whether these observations carry over. Yeah.
So on the very right hand, you have all the nodes are hipster. So they all like see how others like choose. So why you didn't end up with 50-50 again?
It's a nice question. And if we take the case of no delay, we do get 50-50. So the idea is that the nodes in this case have delayed information.
Like, are they oscillating like between two pressures, so they're actually not like steady?
So they are steady.
They are steady.
But so in the first case, so if you don't have any sort of delay, they always choose their behavior always evens out the total distribution. But if they do have delay, then maybe they think that one product is actually the most adopted, but it is really the other one. So it's not sure that they will even each other out. You will get a 50-50 distribution. Yeah, but intuitively, that's what they want to write. They want to even out the distribution. Yeah. Okay. So we'll carry on to 3 regular networks with the same kind of thresholds, and in this case, we again see a rapid increase for small probabilities in the number of fraction of nodes that end up adopting the anti-establishment choice. And for absolutely no delay, we still get a flat distribution here. We are totally even out, as was just suggested from down here. Now, what's different about 3 regular networks is that, first of all, the fraction of hipsters that are needed in order to get 50-50 distribution is small. It's only 6%. So we only need 6% of the nodes to be of this hipster type in order to get a 50-50 distribution of products as time goes to infinity. And if we increase the delay a little bit, then we also see that we don't get as much variation in the fraction of nodes that adopt each product as we did before. These 2 plots look very much the same. And increasing the delay sort of supports what we saw before. We still have the rapid increase, still gets to 50-50 at around 6%. And then we have these this non-trivial, non-monotonic behavior of the product adoptions afterwards. And our analytical approximation again has these abrupt jumps that we don't see in the simulations. Okay, so we observe the same thing. Again, we need only a very small probability of being this kind of hipster node in order to get 50-50 distributions. And in addition, in this case, on this specific kind of network, we don't see a really difference between no delay and very small delay. Okay, so the last synthetic network that we'll look at are Erdős-Rényi networks with an expected mean degree of 5. And you know the procedure. We just do a parameter scan of this network. And in this case, we again get a really small fraction. We get a really rapid increase, and thereby a small fraction of the hipsters needed in order to get 50-50 distribution of products. Here we only need around 7% to be hipsters. And again, we get out jumps, and we get this non-monotonic behavior, and we also get an increasing peak at the of product to options delay. Okay. Although, but then, okay, so maybe I'll just say that the analytical approximation does even worse here. Down here, for example, it predicts that product 1 should be the most adopted of your probability. So great calculations there. Okay, so now we'll jump back to the Facebook 100 network. I was talking about, as I said, a little more than 10,000 nodes. In all of the others, we have 10,000 nodes exactly. And in this case, well, the general pattern persists with an increase in the beginning and then flattening out for no delay, and the same increase and then oscillations afterwards. But in this case, it's less steep and more complicated. We also see that this peak right here increases with the delay. Yeah, so that's how it looks on the non-synthetic level. Okay, so just to conclude a little bit on what we did. So did we save the world in this talk? No, we didn't, not at all. But we did investigate whether it is necessary for a large, at least in these classical spreading schemes that are very well studied, whether it's necessary for a large fraction of nodes to choose differently, to choose the opposite of the majority, the established choice in networks in order to get an anti-establishment majority. And that this was not the case, that actually in all of these synthetic networks we needed less than 10% of the nodes to have anti-establishment opinions in order to get the final anti-establishment majority in this spreading scheme. And apart from this, we got these interesting non-monotonic behaviors and analytical approximation, which we could have done better. Okay, so where to go from here? This, of course, is a very small toy model, but it is easy to extend, like what the threshold model was. For example, what one can choose now, as we were just talking about, how correlations in who has the hipster probability or the hipster behavior and who does not, how this affects the network. How do large broadcasting systems and stuff like that affect these results? Yeah, okay, so this is not published yet, and if you guys have been looking at this thinking, oh, I wish they did this, then please come and say that to me, how to improve the work or how to do things differently. Okay, so I just want to thank Mason, of course, whom I did this with, and we were not with. And then, of course, I want to thank the University of Oxford Mathematical Institute for letting me stay there and do this project and another project. Okay, thank you guys for turning up.
So like in classical marketing, when you try to advertise something on social media, you like really want to like spread off diffusion so anyone can see and adopt the product. And there are like lots of Kickstarter projects that are targeted definitely for hipsters, like the typewriter type of keyboards, all these things. So do you think like you can collect the data about those on social media and how people are adopt, or is it like for them?
Yeah, I mean,
I don't know. Same marketing strategies work as well in these cases, or they are doing something totally different?
So this is obviously a toy model which has probably very little to do with like big dynamics out in society. But yeah, sure. I mean, so I think there are many different applications that one could think of with these kinds of nodes that want to act different than the majority. I talked to a guy in Hamburg who wanted to extend the model to climate activism somehow, and maybe it would be possible to do it with social media advertisement as well. Yeah. Except that, as we saw on social media networks, it was more difficult to turn nodes to get an anti-establishment majority than in the synthetic ones. Yeah. More questions? Okay. Thank you so much, everyone, for showing up.